So today we are talking about chapter 6 on the topic of telescopes. This is the last of our introductory topics. After this, we will be getting into real specific ideas in astronomy. So we're done with the basic introduction and we can start surveying ideas, whether that's types of planets or stars, galaxies, whatever. So we are wrapping up the introduction. Okay, looks good. It's two last adjustments and we are good to go. So what is a telescope? It's a thing you look at space with, right? So it's a device used to observe astronomical objects. A very bland definition, right? I guess it kind of matters because there are, no surprise, based on what we talked about in chapter 5, different types of telescopes. There's visible light telescopes and there are invisible light telescopes, which is just any, telescope that looks at other parts of the electromagnetic spectrum than visible light, such as radio or X-ray or microwave, right? But what do telescopes do? Well, all of them gather light. Okay. We mean by gather, often that means it concentrates light or it uses some sort of time delay. So, so we could have like light building up over time. Think of that as a long exposure, like you would do on a camera, because if you leave a photoactive, sensor, or historically a photoactive paper exposed to light for a longer period of time, then it becomes more highly exposed. Well, that's a way that you could see things that would be too dim to see with the naked eye because we don't have that ability with our eye. We can change, our sensitivity to brightness, but we can't just absorb continuously and overexpose our retinas in the same way that we can with sensors and paper. We are looking at, at light and other types of electromagnetic radiation. Notice the terminology. There's no really agreed upon way whether when we refer to light, we're talking about everything in the electromagnetic spectrum or not. Okay. I know that might be frustrating to some of you, but that's just the way it is. I tend to use light as a general term for all types of electromagnetic spectrum, everything from radio waves to gamma rays. I'm not alone in doing that. That's to call that all light. Some other sources, some other individuals will tend to reserve light for just visible light. I don't find that necessary since visible light is visible light. It's in the name. So at the same time, I also refer to radio waves as radio waves. And I might not say, radio light, right? I just call them radio waves. And so that, it's all kind of, there's a lot of context and different use of terms. To further complicate the matter, but I'm not trying to scare you, just pointing it out because honestly, once you get used to it, it's not that bad. But on top of all that, remember, we also refer to light as radiation. And that term that is really a technical term, right? That's a scientific term. You don't use it in everyday language, but it gets really widely used in textbooks and websites that refer to the technical aspects of astronomy. They call light radiation. So there you go, right? So you got to remember light is radiation is light, the whole EM spectrum is light. Anyway, telescopes can focus light. So you notice that they mentioned gathering and focusing, and it's kind of those are kind of two separate aspects of telescopes. They they focus. Focusing is part of the magnification process. I'll mention that, and I think the next slide or the slide after that. That is an important aspect of mostly visible light telescopes, although some amount of magnifying is relevant to other types of light, but it's kind of harder to quantify, and we don't think about the image getting bigger necessarily. Um, that said, magnification is not the main focus of telescopes. Just making something bigger might be gratifying if you're looking up into space and you notice Jupiter, right? You look up at the night sky and you see Jupiter is just a little dot that you can make out in the sky. Looks like a star, right? Maybe, particularly bright star, but just looks like a dot. You get out a telescope, like a hobby, small telescope, and you look through that telescope, and now you can see that Jupiter has moons. You can clearly see the moons of Jupiter. It's not just one dot, it's a dot with other smaller dots, lined up around it. And you might not be able to see all four of the large moons of Jupiter, but sometimes you can. Sometimes they're behind Jupiter, or maybe your telescope's not powerful enough. But regardless, you can see them, some of them. Well, what have you done, right? You've magnified the image. You've magnified that one little dot into something where you can see more of it. Same for Saturn, right? You magnify that little dot of Saturn into a bigger dot with a clear, blurry ring around it, right? Because you can't really make out like a beautiful high resolution ring with a hobby telescope. That, like I said, is a neat thing to be able to do, but it's not the primary focus of a telescope. Just that little amount of magnification you can do. It's more about being able to gather and concentrate the light and see things that would otherwise be too dim to see. So that's mostly what you're doing with telescopes, although you do a little bit of that enlarging. Okay. And even notice in the next bullet point, allows for observation of fainter objects. Not, the focus isn't really on smaller objects, but on fainter. That's even more relevant when we talk about stars, because no matter how good your magnification is, you're never going to get that star into anything other than a single point. There's no way to resolve the actual angular size of a star. We can kind of resolve like the angular size of orbits around stars, but even that is just the very limit of what amount of magnification we can do in terms of the absolute resolution limit of telescopes, and that would only would be for space-based telescopes, and because otherwise the atmosphere doesn't interfere too much, and it would only work for the nearest stars. So basically, for practical purposes, every star will always just be a single dot, no matter how good your telescope is. But if you got a really good telescope, you can see a lot more of those single dots, right? Because otherwise they'd be too faint to see. Mhm. Okay. And obviously, you can turn galaxies into more than a single dot, which is actually kind of, well, I don't want to get totally off the rails, but I'll kind of I'll circle back around to that if we get a chance, because there's a good reason why. Yeah, a galaxy can actually be resolved into a pretty detailed image. Okay, so for quick history about the invention of the telescope. So obviously, before was any discussion about telescopes that looked at X-rays and radio waves and infrared and any of that, because none of that was known to early scientists, the visible light telescopes were invented back in 1608. As we talked about, they were not invented by Galileo, but they were invented within his lifetime. And so he heard of the invention in 1610, purchased one of these telescopes, which are being used as both actual telescopes that we think of as, because that term gets used for looking at things in the sky, and also as periscopes for looking at, say, other boats across open water, right? So they were basically being marketed by these craftsmen that were making them, right? Because it was this new invention, and it was something sought after. They were rare and valuable, but it was like you imagine, just a high quality, new invention that people were selling on the market. He was the first to observe the sky and record his observations. Okay, so first to do the observation combined with the recording. And he was doing it with that Copernican model in mind. Remember, he was trying to confirm the heliocentric model. And so he had particular goals, which really kind of probably drove his observations and made them have the historical resonance that they have, where we can, see how important they were. He confirmed the phases of Venus matched the Copernican model, not the Ptolemaic model. He confirmed that Jupiter had moons, which was not a necessary condition of either model, nor was it predicted by either model. But what it did is it showed that not everything orbited Earth right there. If there were separate bodies that orbited, one of the planets, well, that right there, brings into question the whole, like importance of Earth as the center of the universe. So, how do telescopes focus? Okay. Well, you could have a telescope with a prime focus, so just a single focal point. All right. And that would be shown in the case of this a reflecting telescope of the top of the three images, where rays are coming in. These would be light rays coming in, bouncing off of a mirror, which it has a slight curvature, either circular or some other curvature, and a focus point being reached by those reflected rays of light. Okay. A flat mirror does not have a focus point. You have to have a curved mirror to have a focus point. Um, Parabolic mirrors are well known for having a very accurate focus point, but circular mirrors are also regularly used for focusing, as are lenses. Okay. But although there are plenty of telescopes that use lenses, including the first ones, like the ones that Galileo was using, and the idea of using lenses to see things that are far away is still widely used in binoculars, for example. And by the way, a good pair of binoculars is a decent tool for looking at the night sky and be able to see things. You can modern astronomy of with visible light telescopes primarily uses mirror-based telescopes. They don't have to be so long. There's a lot of engineering advantages to using mirrors instead of just lenses. Another type of focus for a telescope is the Cassegrain focus. This involves a secondary mirror that reflects light through a hole in the primary mirror. So the initial reflection is the same. However, instead of having a focus located kind of basically in the middle of the path of the light that's coming, from the stars, from the sky, you have a mirror located somewhere internally in the column of the telescope, in that big cylinder, which is the telescope. And that secondary mirror bounces the light back so that the final observer can be at the end of the telescope. Because notice that with the prime focus type of telescope, your final observer, and there may be some additional optics involved with the final observation, maybe another mirror or another lens, but sometimes another mirror just to bend the light at a 90-degree angle in order to have it come out of the side. But in the case of the prime focus, you have to have the observation, like the place to put your eye, kind of halfway along the cylinder. And if you look at telescopes, you can see that often in the less expensive, but most basic type of hobby telescope, you'll see that the observation viewer is about halfway along the length of the column of the telescope. Whereas when there's a secondary mirror, the viewer can be at the very end, which can often be more convenient to, kind of like mount on a tripod and so on. You can even have a Newtonian focus, where the secondary mirror reflects the light out of the side of the telescope. Okay, as shown. So the powers of a telescope, okay? Well, the light gathering power depends on the square of the size of the primary lens or mirror. So that tells us that the larger is better. And that's why there's always been a race for bigger and bigger telescopes. It's not just that, scientists want to show off by having the biggest telescope. There's just a direct scientific significance, a meaningful advantage to having that bigger telescope. You can get a lot more of this light gathering power. Because when you think about what the mirror is doing in the case of a mirror, right? And the same logic would apply to a lens. If I have a bigger mirror, I have more and more rays, right? So therefore, more and more energy that's being focused on a single point. It's still being focused at a single point, but if that mirror is bigger, well, then I've got more concentration, more energy being concentrated at one point, which means I can see something that's fainter than I could otherwise. The resolving power depends on the size of the primary lens or mirror. All right. And notice that it doesn't depend on the square of the size, but just on the size itself. And this tells us that a larger lens or mirror will have a smaller resolution, which means better resolving power. Smaller resolution means that this thing that you can resolve is smaller. So when we talk about smaller resolution, it means that you've taken your minimum size that you can resolve and made that minimum smaller, which is what you want. So you can see smaller and smaller things. I often think of resolving power, and this is the way I've often seen it described, as the the smallest distance that you can make out two separate objects. So if you got two stars, for example, which could be two dots, and they're right next to each other, and if I want to think of resolving power, right? So if I have, dot number one, and then I've got dot number two, well, the distance between them is my, kind of like just a value would be in, meters, centimeters, millimeters, and I call that my R, right? Well, if my resolving power lets me see this separation distance and notice that they're two separate objects, that means I have a small enough resolution to discern and identify these two dots as, as separate dots. And that's so relevant because often there's two stars that orbit each other. They're called binary star systems. They're actually incredibly common. Half of the stars in the galaxy are in binary star systems. We just happen to just orbit a single star, right? But there's a 50-50 chance that we wouldn't, And so, when you look, it just looks like one dot to the naked eye, but it's actually two stars orbiting each other. And the only way to be able to know that is to have a I almost said high enough, but to have a small enough resolution. Okay. So that's your resolving power. So if your resolving power was like this instead, if this was my resolving power, well, that's so big that I wouldn't be able to identify two separate dots, and it would just look like one big blurry dot. So so that would be, I couldn't tell, trying to make it kind of look blurry by being less dense. So I would just notice one big dot instead of two separate dots because my resolving power is not small enough. And last, which I already mentioned in passing, was the magnifying power, the magnification offered by the telescope. And this depends not at all on the size of the lens or mirror. Instead, it depends on the focal length, which is the distance between the mirror and the secondary mirror or between the two lenses. Because with lenses, you're always going to have, realistically, two lenses at least for a basic telescope, sometimes more. And so the focal length is related to the curvature of that lens and how far apart they are. But it wouldn't depend how big they are. So this idea for magnification is totally doesn't demand large lenses or large mirrors. So if astronomers were only interested in magnifying, you know, the objects that they saw in the sky, they would never worry about building big telescopes. But since that is not their main, concern, then we strive to build bigger and bigger telescopes in order to have higher resolving power, or rather smaller resolution, and higher light gathering power. And the counterpoint to that, the last thing I'll say, is that if you think about a compound microscope, or like a microscope like you'd see in a laboratory or a doctor's office, or a medical lab, then with microscopes, the goal is almost exclusively magnification power. There, it's all about being able to make things bigger. It's so for the typical microscope, the focus is the focus. Unintended pun there, because the priority of making a good microscope is that focal length. So you don't need big lenses on a microscope at all. You just need good high quality lenses with a very specific focal length. So there's no need to make your microscope any bigger because you don't really care about the light gathering power. Resolution can be an issue, certainly, but it ends up being that when the resolution matters, you've hit the limit of the visible light limit anyway. So it ends up being not it doesn't matter because you can't see things with a microscope that are smaller than the wavelength of light. And so when resolution would start to matter, we have to use different types of microscopes other than visible light microscopes. Because yes, that's a thing too, right? That's where you come in, you start using electron tunneling microscopes and electron scanning microscopes, which are not at all relevant to astronomy, so we won't talk about them. So limitations, okay? Some major limitations that you almost can't avoid when working with a telescope are the following. Chromatic aberration. This is the idea that different colors bend differently. This is actually what we briefly mentioned when we talked about why lunar eclipses are red. Remember the different colors that enter the atmosphere that compose white light from the sun? They bend at different rates in the atmosphere, and it's the red light that bends the least, and therefore makes it furthest through the atmosphere. And in the case of a lunar eclipse, then reflects off the moon in order to be seen by observers on Earth. Well, that idea of different wavelengths of light, different colors of light bending differently is true of any transparent material. Sure, the gas that makes up the atmosphere, also the glass that makes up a lens. You always have this effect, and it's going to happen to some extent with reflection as well. You're going to end up with some amount of different color dependent or wavelength dependent reflection properties. And what that causes is a separation of the colors. So you end up having images that aren't in focus. They almost look like some like cheap printed comic where like the red and the green don't quite line up. You can tell there's like an offset between them, right? Well, that can happen with images as well. The limitation in size, right? So you have to be able to support and move the telescope. You need it to not collapse or crack under its own weight. So you need it to not deform under its own weight because obviously the exact geometry, the curvature of these lenses or mirrors is crucial to their functionality. So if you make them really big, well, they can get really heavy. And how do you make sure that actually is, first of all, practical, and then second of all, not going to lead to some, unintended just failure of the device. And then, just seeing through the telescope because of the blurring effect of the Earth's atmosphere. So just the limitation that when you are using an Earth-based telescope, you're burdened with the reality that you're within this big sea of gas, which we call the atmosphere. You're at the bottom of it, so the light had to pass through it to get to you. And just being in that environment rather than in a vacuum means that you have to, account for being surrounded by atmosphere. All right. So this is just showing a picture here in terms of the turbulence in the atmosphere and how it can change the way that the light passes through it. Because there's going to be some refraction, which is the bending of light, because and different densities in the atmosphere are separating the light. All right. So one technique that improves the ability of astronomers to use telescopes are active or adaptive optics. So we can build thinner and or segmented mirrors that are going to be able to be moved by high quality motors that can adjust the curvature, account for some sort of deformation that's happening. So we can instead of trying to just make the system strong enough and rigid, we can say, okay, well, we can make it non-rigid and account for things. Have it, have a system that's going to make measurements, find out where the error is, and then make adjustments to compensate for those errors. And that's such a that statement right there is like so applicable to much of the modern world, that so much of our innovations are on this idea of things being adaptive. We do it with sound. The very way that you're listening to me right now involves all kinds of adaptive sound filtering. People like, they they notice, like, that you can hear someone and you don't hear a lot of background sounds. It's because they're being filtered out, but they're not just being filtered out in a static way. They're being filtered out in an adaptive way. There's measurements being made by a computer and then a correction made based on those measurements. So that's, and it's all done at, very fast sampling rates. And as you improve that sampling rate, as the processing power improves, you can just get more and more, you know, doors opening in terms of what is possible. And that obviously is, all about this computer controlled idea. Yep. And then you can even, if you can make atmospheric measurements, right, and know that there's some sort of turbulence happening because of of the winds at higher altitude, right, some 60 miles above the surface of the earth or whatever, you can account for those conditions in your lens by actually changing it dynamically. But ultimately, if you want to have the best telescopes possible, I started to say, if you want to have the best telescope in the world, it can't be on the world. You have to put it in space. So that there's no replacement for a space-based telescope. Ultimately, getting out of Earth's atmosphere has a whole range of advantages and is the paradigm, the ultimate goal of the best telescopes is to put them in space. That said, the majority of them aren't going to be in space because of the expense and the difficulty of doing so. So we're still mostly building telescopes on ground with the acknowledgement that the advantages of space are real and can't be overcome or simulated with ground-based telescopes. So we got some early modern astronomical telescopes. So considering some like that, the Hale telescope at Mount Palomar in California, completed in 1948, with a 200-inch meter, which 200-inch mirror. I don't know why I said meter, other than that, maybe that word, seeing the word in the parentheses, it came out. But anyway, the 200-inch mirror, which is equivalent to 5.1 meters, or about 15 feet, right? Really kind of set the standard for even telescopes today. We're building bigger mirrors, but this is a big change from what you would have seen in the 19th century. And so when you think of modern telescopes, even though this one is, well over 60 years old, or well over 70 years old for that matter, it's, still like, representative of a modern telescope, just an early one. Here we have the Very Large Telescope completed in 2000. It has four 8.2-meter mirrors. And there's a there's one that's ongoing. I believe I should have checked, but this is the telescope that was built by the European Space Agency, who have close ties with South America. They do a lot of their both rocket launches and observations in um, uh, coordination with South American astronomical organizations, and that's where this is based. This is in Chile. There are other very there's the a new project that's underway to build even larger mirrors. So it's a continuing evolution of engineering to build bigger telescopes. Here's the large binocular telescope. So, almost working like a pair of binoculars, like you had to hold to your face, completed in 2004 with two 8.4-meter mirrors. That's so each mirror is over 25 feet across. Right, so huge mirrors. Right, pretty neat looking telescope, honestly. The Gran Telescopia Canaries. So I'm guessing in the Canary Islands. It has one 10.4-meter mirror. And these are all visible light telescopes. We haven't talked about other types yet. And we have this was the other one I was thinking of, the European Extremely Large Telescope. Um, and this one is projected to be completed in 2025, although I know it's still not completed, which is often the case, that these projects are, 10 years or more behind schedule when everything is said and done. and it's going to have a single 39.3 meter mirror. So I mean, it's really, you know, a whole nother scale of mirror. More than tripling the size of the biggest mirror that's been used before. So I talked about the limitations of being in on Earth, but I realize we are due for a break. I'm not too late, luckily, but I was uh, I was going to check, and I didn't think so much time had passed. But this is good transition. So when we get back from our break, we'll talk about kind of a summary about what it means to be, you know, taking observations within the atmosphere, so ground-based observations, some why that matters, and relating that idea to the electromagnetic spectrum and the different types of light, so not just visible light, and to use that discussion and this figure as a transition to talking about both space-based telescopes and telescopes that observe other types of light. So we'll take that concept on after a 5-minute break. Okay, so continuing with our discussion of telescopes, we've got a slide here discussing transmission through Earth's atmosphere. All right, how do we get here? How does this matter for telescopes? Well, you might see in the figure that we actually see some named telescopes shown. You also might notice that they all look like satellites because they all are. But let's talk briefly about why. I'm going to zoom in a little bit so we can see real clearly. Okay, that this figure shows the ground, right? So we have sea level. And that's because we're thinking about observation points where you can put a telescope in order to see things in the sky, in order to look into the cosmos. All right. And we also have across the horizontal axis all the different types of light that compose the electromagnetic spectrum, from the very short wavelength, high energy gamma rays, also short wavelength, high energy X rays, to ultraviolet, pushing up right to the narrow band, which is visible light, moving into lower energy, longer wavelength, infrared light, all the way into radio. Radio and microwave are just kind of included as one category here. And in each of the cases of the types of light, there are these drop down arrows which show how far these different forms of light, these different forms of electromagnetic radiation, how far they penetrate Earth's atmosphere. Since Earth's atmosphere is a gas, different types of light are going to make it through that big pool of gas, that big ocean of gas, differently. And mostly this comes down to the same principles that we discussed when we talked about absorption and emission spectra. So the atmosphere is acting in the same way that a cloud of gas acted when it was in front of a continuous spectrum. And namely, it's absorbing some of that energy. It also we have cases of what's called scattering. Scattering is basically just absorption followed by re-emission. So it's just the same principles of excitation of a molecule or an atom and then re-emitting that light when the atom or molecule relaxes to its energy ground state. And what happens is that released energy is in any random direction. So that's the scatter. So light comes down, right, and comes straight down because it's coming from a certain source. But when it enters the atmosphere, it gets scattered in any direction. Well, that means that very little of it is actually going to make it to the surface, right? Because then the chance of it getting scattered back downwards is small. So then we end up not being able to see things after many subsequent scattering events. Sometimes the light gets absorbed and re-emitted as a different wavelength. So in that case, we've completely lost the information that the original light carried. But whatever is the physical mechanism, much of light that comes from space does not make it to the surface. In many cases, that's a good thing. And I laugh because literally the reason that we're here today is because of the atmosphere. Atmospheres have a very, very important role to play when it comes to preserving life. When astronomers look for the potential of life on other worlds, they look they look for the potential of atmospheres for exoplanets, there's planets that orbit other stars, and they also, within our own solar system, they focus on these subsurface oceans on some particular moons that orbit the gas giants, which we will talk about when we talk about Jovian worlds. And well, that's because those subsurface oceans are protected because they're underneath a sheet of ice. And protected from what? Protected from space. Well, what does that mean? So yeah, sure, space is a vacuum, which is not great to life, but that's not what I'm talking about being protected from. Space is full of really high energy light. Space is full of X-rays and gamma rays in particular. And if you're in space without some sort of protection, some shielding for X-rays and gamma rays, you get radiated. You get cooked by the X-rays and gamma rays. And if you don't get cooked, you at least get, irradiated in the sense of having very significant cellular damage, which is going to cause, organ failure down the line. And so this is a major concern for astronauts. They have to really, be within shielded areas when they're in space. And there's certain regions of space that are even worse than others because of the sort of especially in the case of some charged particles and the what's create and the byproducts they create. They sort of channel some of them. You have these like the Van Allen belt is known for that, which is a certain distance from Earth. But all that aside, just in general, space is full of high energy light. But luckily, it doesn't make it to the surface of an atmosphere like Earth's. Okay. It's also a big concern for any projected base on the moon, where there really is no protection, or even on Mars, where there's very little protection. So if a person was to live on the surface of Mars, they would either have to, be within some sort of like, good shielding, like thick metal shielding to protect them from all the X-rays that are bombarding the surface of Mars and passing through Mars's very thin atmosphere, or live underground, realistically. And because you couldn't just operate on the surface of Mars in the suit, and not die within a few years, to be quite honest. But Earth, we're good. We got our thick atmosphere, and we see it, right? We see gamma rays, X rays. They just can't make it through the atmosphere. All right. They are more common in the upper atmosphere where you could, have like a weather balloon or a high altitude rocket or even certain planes. All right. So but if people are up there operating in a military jet, they keep that in mind. And if you did want to make an observation of gamma rays or X rays, you could potentially do it with a very high altitude weather balloon, for example. Okay. Some actually really early science that started to explore this phenomenon was done with just basic early hot air balloons and a X-ray detection device in the 19th century, and just going up a few kilometers above the surface, there was a noticeable increase in the number of X-rays. So you can see that, I mean, even that the 40,000 feet you fly in an airplane, there's much more X-rays up there, but they're not going to be making their way into the cabin of the airplane. Okay, so can't see them on the surface, however. So because of the protective nature, it also means invisible. You cannot have a ground-based telescope that's going to be looking for gamma rays and X-rays, and that precludes a whole amount of you know astronomy and scientific questions that you might want to answer. Because there's a lot of important phenomenon in space that produce gamma rays and X-rays. And if you want to explore them, you can't do it on the ground. You have to have a observation telescope. You have to have a space-based telescope. So any telescopes that survey gamma rays and X-rays are orbiting satellites. So they are satellites in orbit, along with all the communication satellites, and everything else that's up there in space, all the GPS satellites. Among them are actual telescopes. Big expensive projects, highly refined instruments and measuring and then sending with some sort of like uh, direct connection to the ground, sending the signal back down with another wave, right? But the communication line between the satellite and the Earth would be using radio waves. And that works because if you check it out, if you go all the way up to the other extreme of the electromagnetic spectrum and you look at radio waves, you see that radio waves do penetrate the atmosphere because of their length and the fact they don't scatter very easily. They're able to pass through a gas with very little disruption. So their length is an advantage for their ability to pass through things, which is why when I mentioned light and talked about very long radio waves being used for like submarines and communications underground, that's because when they're even longer, they can even pass through rock and water. But through a gas, a typical, meter long or so radio wave is going to be able to penetrate the atmosphere and cause, communication back and forth between satellites. It's a good thing radio waves can penetrate the atmosphere because that's the way our whole satellite system works. We're able to communicate back and forth with satellites via radio waves. Okay. What else penetrates the atmosphere? Well, infrared and some microwaves don't really. So there's kind of you can see there's a range here where once you get shorter than radio waves, that you again have absorption happening closer to the ground than gamma and X-rays, but not at the surface. That has actually led to some plane-based telescopes. There was a famous telescope operated by NASA for decades that was a infrared telescope, so looking at infrared light coming in from space, which was really crucial for big questions in astronomy, both really old galaxies and for the study of exoplanets and looking at like planetary disks and things like that. When solar systems are being formed, which are called protoplanetary disks. But anyway, this plane-based telescope would, take off, fly up, fly at a certain, determined altitude on a particular path, and then it had all these kind of stabilization built in. It was basically a 747 that was just completely converted into a telescope observation station. And then they would open up the side of the plane, and they had a big telescope that would be there, and then they would take their observations during a flight until they ran out of fuel, and then in that observation day. It eventually ended up being retired because everything that it was able to do could be done just as well by space-based telescopes. And yeah, not more cheaply on the upfront cost, but in the long run, more cheaply, because once we get a space-based telescope, we have a very long operation life, and we don't have to continue to take it off and refuel it and deal with constant corrections and so on. And then actually is a kind of takes me to these two of the most famous space-based telescopes, Hubble, which is a telescope that orbits Earth and has been crucial for our understanding of deep space and also made astronomy accessible and popular with the public in terms of its high quality images. And much more recently, the JWST, or the James Webb Space Telescope, which doesn't orbit Earth, but actually orbits the sun at a special point called the Lagrange point, which is on the far side of the moon. And it is a revolution in terms of the quality of the telescope and its ability to operate mostly in the infrared, although it does have a little bit of ability to operate in a little bit into the visible range, but it's primarily an infrared telescope and in space. Visible light does make it to the surface of Earth. That's why we can see it. Talked about the evolutionary, explanation of our eye's ability to see visible light. It's just this particular bandwidth that our atmosphere is transparent to. So if you can see, it's kind of just a quirk of the particular composition of the atmosphere that it's transparent to this type of light. And it makes its way to the surface. We can clearly see it. And then, of course, we can build telescopes that can observe it. When we build telescopes, we try to build them not at sea level, but at higher altitude to eliminate some of the atmosphere and to eliminate some crucial, um, you know, detrimental aspects of the atmosphere in terms of like high water content that tend to concentrate at or near sea level. This is kind of our summary. The last thing that I didn't mention was that because of radio telescopes or radio waves' ability to easily pass through the atmosphere, that means that we can also take advantage of that, and not just for satellite communication, but to have radio telescopes. And so there are lots of ground-based radio telescopes, and it's a fair statement to say that the field of astronomy that has the most potential of growth for telescope observation at the ground are radio telescopes, where we're pushing the limits of what we can do with visible light telescopes with those biggest mirrors, and there's not too much more that we can do. We can continue to use them and make observations, but they're not going to get much better. But we can build better and better radio telescope basically arrays. We can build big networks of radio telescopes. And since it doesn't really matter at all if they're at the bottom of the atmosphere, because the atmosphere hardly interferes with the radio waves, we can really improve that ability. We can almost turn whole continents into radio telescopes in the future, potentially, because we can have whole networks of radio telescopes that are, with some sort of fiber optics almost instantly communicating with each other, and then having that whole system act like a single bigger radio telescope. So there you go. Probably a little long-winded, but that's our big summary. A lot of neat ideas about what telescopes work on the ground and which don't. Okay. And then the quick summary: only radio and visible light passes easily through Earth's atmosphere. We need telescopes in space. So radio telescopes, I just wanted to do a rundown on them, and then we'll finish with a particular space telescope. So like visible light, radio waves can penetrate the atmosphere and be observed from the ground. This gives us an entirely new view of the universe, right? So we're not looking at the visible light signal, we're looking at the radio signal. Radio waves are not sound waves, okay? They can't be heard. Radio, we think of it as sound sometimes because, you listen to the radio, it's sound, right? That's just because the signal is converted to sound, okay? But the signal is light. Early radio astronomy was done back in the 1930s. It came out of like military radio communications because this was really the dawn of radio. It coincided with the dawn of radar between World War I and World War II. That's really when this stuff was invented. It wasn't known in World War I by any maybe outside of a few scientific circles that you could really use radio waves in the way that we think of them today. In that study of radio communication, right, for commercial and military purposes, this person Karl Lansky found radio waves from an unknown source. All right. And they appeared 4 minutes earlier each day, which is the sidereal period of Earth. And what he was able to find was the galactic center, because he was able to see that this signal wasn't coming from within the solar system, but was instead a radio signal coming from the center of our galaxy. And then that's when we started thinking, well, what could it be? What at the center of the galaxy is producing a radio wave? Well, it turns out that there's lots of different things that can produce radio waves, but black holes are one of them. And so, with radio waves, we can study really cool objects, so things that are very low energy, so molecular clouds that have very slow motion and create radio waves through a version of black body radiation. And we can also, on the whole other end, explore incredibly energetic objects, because around things like black holes, there are electrons that are accelerated to these incredibly fast speeds, a significant fraction of the speed of light. And in doing so, their acceleration paths act like giant antennas. So you have these plumes of gas with accelerating electrons in them that are acting like big cosmic antennas. Well, what does an antenna do? An antenna produces radio waves, right? And so we actually have these naturally occurring antennas that produce radio waves that can identify a black hole, and show us, especially the types of black holes that are found at the centers of galaxies, which are called supermassive black holes, and are at the center of every galaxy we think, and have confirmed many of them. We have one in our own galaxy. So, that's a whole fascinating idea about what you can do with radio waves. And then a whole other thing that's done with radio waves is that they are used to study the very beginning of the universe. They're crucial in our understanding of the Big Bang. There's no more important discovery and evidence of the Big Bang than the cosmic microwave background radiation. And obviously that's a microwave, but still radio wave by some definitions. And it's this signal that's left over from the Big Bang. And we'll talk about how that is the case when we get to the big chapter on the Big Bang. So advantages, of the radio waves, they can, observe day and night because, doesn't matter if the sun's up because they're not looking at visible light. You get a very different view of the universe. So, obviously you can't answer questions that require visible light, but there are other questions that you can tackle. And often you can think about how to reformulate things. What else can radio waves tell us that we don't even know yet, right? Because there's always room to think about things differently. They can easily penetrate dust in our galaxy, so that is actually why they were discovered coming from the galactic center, and we'd never seen anything else coming from the galactic center because up until that time in the 1930s, if any astronomer turned a visible light telescope in the direction of the center of the galaxy, they didn't see anything. They just saw a dark region, right? When we look at the Milky Way, it's this cloud across the sky, right? If you're in a really low light pollution area. Well, if you get a telescope and you look into that cloud, you see some stars initially and it just becomes opaque because it's too much dust for visible light to pass through. Well, the same way that radio waves pass through the atmosphere, they pass through dust. So then we can see that signal that we cannot see with other bandwidths. And we also explore cool hydrogen gases, which is really important for the recycling of matter. This key thing that spiral galaxies do in terms of the star gas star cycle. Essentially, stars explode, they turn into gas, the gas recondenses and turns into stars again, and the process continues until eventually the galaxy collides with another galaxy and then becomes an elliptical galaxy, and then there's no more process anymore. And then the universe cools until its eventual heat death, or maybe not. Obviously, I'm being silly about stuff that we haven't seen yet, but these are all these mini ideas that we will see down the line. Disadvantages. Okay. Well, poor resolution. You can't see things small. So so they're great for seeing really big galactic sized things. They're never going to be an advantage for seeing individual planets around other stars. They just would never have that resolution because they're long waves, right? And there's a direct correlation between the wavelength and the resolution ability. They need to be made very large. So the actual radio dishes themselves have to be very large, and this is really kind of the modern direction of radio astronomy, you have to have these networks of individual dishes that function like a single dish. And you have to, compete with all the radio waves that we're sending back and forth, right? We just have this just maze of radio signals that are just going everywhere, because cellular communication, all our cell phones, that's a form of a radio wave, right? Kind of in the longer microwave spectrum, but still a radio wave. And we've got just radio waves everywhere, more and more every day. So how do you filter those out? How do you reserve particular frequencies or particular wavelengths for astronomical observation, and not have some sort of noise in your system. All right, and then interferometry, I just want to quickly mention, is that connecting of telescopes. Like I want to do it quickly because I've already mentioned it, kind of hinted at it, and it's where you can have all of them, all these individual dishes, as you can see here, because it's worth pointing out, because I don't want to miss this key statement, that this is a radio telescope. Okay. When you see, when you see one of these, you might be somebody that just, still uses satellite TV or has their old satellite TV dish and they never got rid of it. But more, maybe more likely, or depending where you are, it's a telescope. Okay, it's a radio telescope. And so, it doesn't look like a telescope, what we think of, but it absolutely is. The mirror doesn't have to be a reflective surface, like for visible light. It just has to be a curved surface because the waves are big enough that the mirrors can just be kind of like, they can literally just be a mesh of metal rods with gaps between them because if the gaps are small enough, the radio wave won't, essentially can't see them, right? Because it's all a matter of scale, or some sort of just like basic metal covering or like or heavy duty fabric, synthetic fabric or something. So that's your curved mirror is just the dish itself, and the focus is just some sort of sensor that picks up the radio wave. So often there's the big connected sensor that's at a particular position, which is the focus point of that curved mirror. But when you have many of them operating together, you've got that increased effective size. You can really have them all operate like a single dish that is the size from one edge of the array to the other. Okay? So with that in mind, the need to build individual large dishes has become less important because we can really, just work out the details of having the communication be effective between them because that's no small task. But as long as you deal with, having a really good communication system between your individual dishes, then you can have them operate like one big one. But not so long ago, that wasn't an option, just mostly because of the processing power involved, right? To have good enough computers to do it, and so there was still a drive to build really big individual dishes. That's like one we see here. You certainly completed recently, right? But kind of a sign of a past era, 100 meter individual disk. Are there not advantages to an individual disk? Yeah, they kind of are, right? So there's always gonna be some sort of trade-off. And maybe down the line there's going to be some reason, some limitation that the arrays of dishes can't do, or maybe they're good on the really big scale, but we still want to build some, maybe even bigger individual dishes like these. Who knows? Speaking of which, the biggest individual radio dish and radio telescope, right? The dish just being, the curved mirror here, is no longer in existence. It collapsed back in 2016, but it had been for decades the biggest um, radio telescope out there at 300 meters. Um, Made famous by its showing up in a few movies and just having a really iconic look to it since it was nestled in this tropical jungle. And essentially, they built it into a natural depression, right? So they were able to take advantage of the structural, sides of the mountains in order to hang the dish. It was basically just suspended by wires, and then the focus point was here, and this is where the sensor was. But there was a cable collapse, and this thing fell into the dish and destroyed it. It was already non-operational, but was potentially going to be um, modernized and repaired. But once there was a critical failure and the extent of the damage, it was permanently retired with no plans to build it back. So it no longer exists. Okay, so that's enough with radio dishes. Last topic of the lecture, the James Webb Space Telescope. The new Space Telescope just launched a few years ago, and it is a major step forward from the Hubble telescope, which itself was a game changer for astronomy. What the Hubble telescope was just the things that it accomplished, the amount of science that it advanced, just cannot be overstated. It just changed the entire field of astronomy, honestly. And the James Webb Space Telescope it really has an incredible amount of resolution power, of ability to take images that we just couldn't take before. It's allowing us to explore the very early universe because we can look back in time much further than we ever could before. And by much further, I mean that we can now look to the first couple 100 million years of the universe and look at these primordial galaxies, which was nothing we could do before. It just was not an option. It also happens, although it wasn't even in its original mission, goal, is that it's really good at observing exoplanets. It's really good at looking at the signals that are associated with the indirect measurement of planets orbiting other stars. And so it's gonna be able to contribute to the already impressive amount of information that we've gained about exoplanets. It's going to help us identify the atmospheric composition of planets around other stars. And so we can start looking for signs of things like oxygen in atmospheres and so on. And the basically the surveys, the observations that it's taking are that it's going to do are always evolving and changing, because the way a space telescope like this works is that teams of scientists submit a proposal of how they want to use it, how many hours they need to have access to that telescope, and then it gets approved or not, or approved some years down the line, and then the task is finally completed, and that sometimes can lead to a whole new idea about what it's capable of, because potentially no one had thought of using the telescope in that way. And so because of that nature of individual teams and their innovations, you always have this like kind of dynamic process that's happening where the telescope isn't just always being used in the same way, because it's not like it's just a fixed group of people that use it. It's always it's always being used in different ways, and sometimes that where people are startled and just impressed with the new ideas coming out. How long will it be observational or operational, and also taking observations? So I guess observational. Well, 20 years, 30 years. It's hard to say exactly. Often they can extend the lifespan as long as something doesn't go wrong. It was built with a lot of fail safes, and so far it's its launch and startup and first couple years of operation have gone very well. So there's every sign of a long lifespan and lots of data and lots of you know discovery to come. So quick history of it. It was proposed back in the 90s, and then we can see that it was really throughout the 2000s. There's all these milestones in terms of the completion and then actual construction. Fully built in 2016, and then it was launched in 2021. It was launched in going back to South America. It was actually, that was on my mind when I mentioned it before. It was launched from a launch station located kind of near the equator, which is advantageous for certain launches. And it went without a hitch, successfully launched on basically one of the biggest rockets that are currently used, because it was going to a pretty difficult spot to get to. So you don't have to use a giant rocket if you're just trying to send something up into orbit, but that's not where this James Webb Space Telescope was going. It was going out into pretty deep space, so well beyond the moon. Okay. This is how it fits in with other famous telescopes. So you see like Spitzer and Kepler. Kepler was made famous for its extensive discovery of planets around other stars, exoplanets, which of course I've said a few times today. All right. And we can see a trend here in terms of their planned life. So yeah, I couldn't remember this time, but so it's kind of on the pessimistic side. It has a planned operational life of 5 years, but it could certainly go longer. To put that, kind of the extreme case into comparison, Hubble was only planned to operate for 15 years, but we've been using it for 50 years and it's still going strong. So often we can use these telescopes for longer than planned. Of course, with Hubble, we actually did send people up to make a repair on it at one point. Astronauts, were hanging off the side and working with tools to repair and improve some of its parts. That will most likely not happen with the James Webb Space Telescope because it is so much further from Earth. Again, it's not orbiting Earth; it's orbiting the sun. But you could perhaps send a robotic probe out there in the future. All right, and this is some quotes about it. Okay, what does it look at? It's going to be, I'm going to skip over this in the interest of time. And I already told you. It's looking at the infrared. Okay, so it's an infrared-based telescope with a little bit into the visible red, orange, and yellow range. And this is in contrast to Hubble, which is mostly a visible light telescope with the ability to also see infrared and ultraviolet. And another well-known telescope, the Herschel telescope. Okay. Why look at the infrared? Because it was primarily designed to take observations about the early universe. So looking at all this light that has been redshifted. See, so if we look at, and these Z values refer to the redshift value. And so as you go back in the time, the visible spectrum gets redshifted into the infrared. So a galaxy and all the stars that are producing primarily because stars primarily produce visible light. Well, now they're producing infrared light if they are far away. So if you are looking at a star that's 5.1 billion light years away, which is, a big population of stars in galaxies, and those aren't even the most ancient galaxies, not the oldest. Well, they have a redshift of zero point 0.5, okay? And this is referring to the formula, which I won't get into right now. But the point that the figure is telling us is that that whole spectrum has been, shifted entirely into, well, not entirely into the infrared, but entirely into the range of the James Webb Space Telescope. And if we go even further away and thus further back in time to these older and older galaxies, way back to those first galaxies after the Big Bang, we are now solidly in the infrared and really taking full advantage of what the James Webb Space Telescope was designed to look at the ancient universe. And in doing so, really do something that Hubble was not designed to do at all. So we have a whole new goal for the space telescope, to understand what the universe was like when it first started, which is a pretty, amazing question, right? That, because that's, of course we want to understand that. We want to understand that what was the Big Bang? How did it happen? How do we piece together, this information? Okay. So there you go. So infrared lets us penetrate through clouds of dust and gas. Yep. So that's good for the planets. So I'm skipping over some of this. And so that'd be good for looking at a inside of big nebula. So if you look at this famous nebula, often called the Pillars of Creation or the Carina Nebula, we can see in the visible spectrum, huge sections are obscured. They're pretty, but you can't see anything behind them, right? Notice these big sections that are kind of like red or kind of a dark orange yellow color. You can't see any of the stars within them because all of the dust particles are obscuring them. But if we look in the infrared, we can actually see the stars. So they allow us to see within this nebula in a way that visible light would not. All right. And then what type of light is emitted strongly from the BH black hole accretion disks? Well, I mentioned that before. X-rays, primary type of light emitted by Earth, infrared, emitted strongly by cold interstellar gas clouds. That's going to be radio waves. Light making up the cosmic microwave background radiation. I told you that one. Microwaves. All right. So this is the mirrors that actually make up the James Webb Space Telescope. So they had to unfurl after the launch. So they're all based on each of these little hexagrams or hexagons was like an individual piece, and they kind of like had to move afterwards because it was all folded up when it was launched. And then the last thing that I want to mention is where it's located. So I'm going to skip ahead to that. So, okay, this is a cool thing. The last thing I want to finish off for today's class with, we obviously won't get to any other content today, is that I didn't know that discussion of the James Webb Space Telescope would take so long. And obviously I'm skipping over some slides. So, okay, there are these special points for any orbit, and they are created because of a balance of forces in Newton's second law. So what happens is you have a gravitational pull from the orbited body, the sun, and then you also have a gravitational pull from the body that's orbiting the Earth. And usually, we don't care about the gravitational pull from the smaller thing. Although we've already seen times that we do consider it, such as tides, right? So, because normally we just say, hey, the moon orbits Earth. But when we talk about tides, we're talking about the fact that the moon pulls back, which is a Newton's third law type of consideration. Since the moon pulls on us just as much as we pull on the moon, well, that causes objects that are free to move, like liquid water on the surface of Earth, to, get affected. All right. So that type of kind of secondary pull is what leads to the idea of the Lagrange point. And there are 5 points in any orbit, and so in this case, near the Earth, that orbit at the same rate and remain at fixed locations relative to Earth. Because of that balance of forces, they represent these stable locations. And that means that if you put a satellite or a space-based telescope at that location, then it will stay there and it will orbit with the exact same orbital period as the smaller body, in this case, Earth. Okay? So the five Lagrange points, L1, L2, so L for Lagrange, and then just the names. Here are their locations. Not at all to scale, by the way. They are really close to Earth. So like this, if L1 was drawn to scale, you wouldn't see it because it'd be obscured by the oversized Earth. They're always much closer to the smaller body. That said, they are relatively far in terms of the distances we normally talk about for space distances. So here we got L1, L2, all right, and then there L3, which is on the far side of the sun, L4 and L5. Okay, so there they are. The one that has and this is the orbit. See, as we orbit the sun, the Lagrange points remain fixed. See, they're always at those same relative locations to Earth and the sun. So they orbit with us. They're like a system of fixed orbiting points. And are there anything at them normally? Well, maybe like a rock or two, right? Sometimes an asteroid can end up in them, but generally they're empty just by the general kind of, like mathematical argument of statistics, just the odds are that they will be empty. But if you put something there on purpose and you do it meaningfully, and you know that you have to, sometimes account for other small forces that could push something out of there, then because any small force could disturb the location. But if you account for that, then you can put a satellite there, an artificial object. Okay. So where is the James Webb Space Telescope? It's at L2. So it's the opposite side of Earth from the sun. That Lagrange point was chosen because it can now be turned away from Earth, and that means that it will have a permanent view looking out. It will be able to look out at all parts of space as we complete our orbit, right? So we'll have an opportunity to look in any direction because we can always look up or down. It just has to wait a year to do so. And it never has to worry about the interference of light from the sun or even reflected light from the Earth because it can always face out. That was a huge reason why L2 was chosen. Okay? So we can think of it as remaining behind Earth, protected from the sun in a sense. Right? So it's just going to stay there, orbiting with Earth. All right? And because its orbit is larger than Earth, could it take longer to orbit? Well, no, because that's the whole point. Normally, yes, right? If this was not the Lagrange point, if you chose any other point, because this is a very particular distance, but if you chose any other point, then the orbital periods would be different. They'd have to be. That's the way orbits work. Think about Kepler's third law. There's a direct relationship between semi-major axis and period. Well, this is breaking Kepler's third law. Why? Because Kepler's third law didn't account for a secondary force. It's just an extension. Oh, you have to hear me through the microphone now. Headphone died. All right. So, right, it doesn't orbit, right? So, the thing is, right, it has the same period. So it doesn't have to have a greater period of orbit. Okay. It should take longer, but it doesn't. Right? And then in terms of the distance, oh yeah, cool things you can put there. Asteroid mining.
So Lagrange points, will be really important to the future of astronomy. And what I wanted to point out is kind of how much further it is than the moon, but I don't see the value here, and I didn't look up ahead of time. But it is significantly further from Earth than the moon. They give you some idea of how far away it is. Not easy to get to. All right, but I say that that's a good stopping point. Got through key information, and I will stop the recording.